research study named Human Exoskeleton Kinematic Calibration to improve tracking for dexterous teleoperation. In this study, we present a human data-driven calibration method to reduce the error in hand motion tracking in a hand exoskeleton. This video includes two demonstrations. Demonstration 1 illustrates the calibration procedure of the thumb, index, and middle fingers respectively. Demonstration 2 showcases human hand teleoperation in a Unity-based hand simulation environment. So why are we interested in human motion tracking? Well, we believe that hand motion tracking is important for dexterous telemanipulation, while the accuracy is affected by relative position between the human hand and the robot's exoskeleton. So imagine that there's a human operator and he's wearing a hand exoskeleton. If the human operator is trying to do a specific finger motion, let's say thumb index pinch, then without any sound calibration, it is very likely that there will be a large discrepancy between the human hand and the simulated hand, which could be confusing for the human operator considering the visual feedback that he's having there. But with calibration, it is very likely that there will be a good visual alignment and it will be intuitive for the human operator. So what we are offering here is this calibration method. So we are presenting a human data-driven calibration method on the hand tracking by reducing the errors from virtual links connecting the hand exoskeleton link and the human finger links. So this is the specific calibration methods we're presenting here. So firstly, we will use 7 human subjects to search for optimal weight distribution. And then we are involving a new human operator where we offer the optimal weight distribution to the calibration process, which is called two-phase calibration. And now this new human operator is supposed to do 2 motions to do the calibration. One is fully flatten the fingers. The second is bending MCP while keeping the PIP or IP straight. And then the updated virtual links is used to update the kinematic model. So if there's no calibration, let's say when there's a hand exoskeleton motion data tracked, then will be input to the original kinematic model, the estimated human hand's motion will be very likely to have a great offset. While if we have this calibration and offering the hand exoskeleton motion data to the updated kinematic model, it's very likely that we're going to have a high quality visual aligned motion tracking. So this demonstration presents the calibration procedure for the 3 fingers respectively. On the left side of the screen, there's a human's hand wearing the exoskeleton, while on the right side of the screen, there will be 3 fingers connecting both the human fingers and the kinematics links. For the labeling, the red links is for the thumb, the green links is for the index, and the blue link is for the middle. Now, here's the calibration process for the thumb. At the first phase, the thumb is extended, and then the second phase, where the MCP is bending. Now the calibration is done. Now here comes the index calibration. Fully extended and then bend MCP. Now the calibration is done. The same process is repeated for the middle calibration. Now let's compare before and after calibration. Here we toggled back and forth between pre and post calibration. It is worth noticing that because the relative position between the fingers is not considered in this study, there will still be some offsets across the fingertips, but the improvement is very apparent. Now it's the full pre-calibration procedure, and now it's the full post-calibration procedure. Now let's head to the demonstration 2, the real-time Unity-based teleoperation. In this case, the left side is still the human's hand wearing the hand exoskeleton, while on the right, there will be a red avatar hand present the hand motion before calibration, and the green avatar hand is the one after calibration. In this case, we're going to come across 4 different hand motions: fully flatten, thumb index pinch, thumb middle pinch, and 3 finger pinch. Now we started from the thumb middle pinch. Now the thumb index pinch. And lastly, the three finger pinch. Thank you for watching. We're looking forward to your feedbacks.